Hello, good morning. Welcome back. All right, so let's get started. And today, in this lecture, we're gonna cover the logistic regression model. And it is very closely related to the linear regression models that we have already been through, right? But it's for a different type of problem. And in fact, it is a very important basis for building future neural network-based models. Okay, and once we know about the mathematical nature of that's behind the logistic regression model, it'll be much easier and much clearer that modern like deep learning based models, what's the basic building blocks of those so-called deep neural networks. Okay, so a little bit difference from linear regression is that for the case of logistic regression, we are looking at a classification problem rather than a regression problem. So in the linear regression chapter, we use the housing price prediction as the example, right? So price is a number, it's a floating number that ranges from that continuously change. So if it is that continuous number that we want to predict, then it's a regression problem. And in this case, in logistic regression, as we will see later, we actually are in a lot of other more scenarios, we are faced with problems that we want to predict discrete outcomes rather than continuous changes. Okay, like whether it's gonna rain or not tomorrow, right? And like the emails that you receive, there will be a built-in filter that predicts whether one email message is a spam mail or not, right? So all these kinds of binary classifications are actually everywhere in our daily life. And logistic regression model is one of the most efficient and effective ways to handling those binary prediction tasks. Okay, so we will cover these several parts. Let's first start from linear regression, and we will try to find what is the downside of applying linear regression paradigms to the binary classification case, and that will introduce us why logistic regression is a good way to apply to be applied to the binary prediction task. And specifically, we will introduce the cost function of logistic regression, which is different from linear regression. And similar to linear regression, we will implement the gradient descent method for logistic regression. Okay. And lastly, there will be some special notations that are slightly different from linear regression. And also these new notations will carry on to all of our next lectures. Yeah, and I hope we will have time to cover the last part, which is the multiple class prediction problems. Okay. So let's get into the transitioning from linear regression to logistic regression. I think we have already shown this example, right, in the introduction part for linear regression. It's a common problem for predicting to give a binary predictions, like given a picture of a fish, we want to predict whether it's salmon or sea bass, right? So let's think about the problem using the models that we already have, which is a linear model. Okay, so we have some data points available, and we have some features collected. Say we can use the length of the fish, for example, as a feature. So the x-axis here is our feature, and the y-axis is our label. So we would assume that the CBAS has the label 1, right? And well, it's a typo here. I need to fix. Let me quickly fix it. All right. When I added this part, got to change all the text back. So I use red for CBAS and the black should be salmon. Okay. All right. Okay. So we have two types of data points, and we know their labels. Okay. So our next task is to find a model that can distinguish these two classes, that can tell the differences, right? So what about we try linear regression models? We know the prediction function looks like a linear equation, right? Theta 0 plus theta 1 times x. We have two parameters in this case, right? That is the simplest linear regression. And if we fit the model, we train the model like using either normal equation or gradient descent method, it will always give us some trained parameters, which is theta 0 and theta 1, right? And it looks like a line that crosses all the data points. Okay, so that's a model as illustrated by this blue curve or blue line. So what we can use with this model is to use a simple threshold to make prediction, right? In this case, we can use the threshold of y hat equals 0.5. If the predicted value y hat is above, then we will claim that it is closer to the cluster of salmon. While if it's smaller than or lower than 0.5, then it's closer to the CBAS cluster. All right, so it seems a pretty straightforward way, right? But it could be a quite serious problem, right? Because if we consider some new data, say we have some new salmon fish collected, and if we retrain the model, then given this new data, the newly fitted line would look like this, right? Because there are more black dots on the right. So it causes a problem to these data points on the left, because according to the predicted values by the new model, right? These three black dots, black data points, they have some new predicted values that is below 0.5, right? Which causes misclassification, right? They are actually salmon fish, but according to the model, they fall to the threshold, below the threshold, right? So that is a problem for applying linear regression models to a binary classification problem. Okay, so we need to think about the question of how to improve the solution, right? So basically, we want a new function that can generate some outputs between 0 and 1, right? Rather than a curve, rather than a straight line that can extend to infinity, right? And we want a smoother curve, and it should be stable against the outliers, right? We want something like this. If a function have such a curve, right? It's always produce the output between 0 and 1, and there's this like a very smooth S shape that can tell apart the two clusters of the data points. Then that's ideal. Okay, and luckily we have such a function. It's called Sigmoid function. Okay, let's see if we define our prediction function as h theta of x as the g of theta transpose times x. Okay, and the function g is defined in such a way. It is actually 1/1 plus e to the power of negative theta x. Okay, so this theta transpose x is actually a short form for writing theta 0 plus theta 1 times x, right? So it's a linear combination. And of course, we can have more thetas. We can have more than one features. Okay, so this function, g of something, is called the sigmoid function, right? It's defined like given the input z, the output would be 1/1 plus e to the power of negative z. Okay, right. It has the perfect shape that looks like this S shape, and also the range of the output is always between 0 and 1. That's something you can actually examine very quickly. Imagine the z becomes a really big numbers, right? Then the exponential function e to the power of a very big negative numbers, then it's almost this exponential term almost becomes 0, right? So the outputs will be very close to 1/1. And on the other hand, when z equals a very small negative number, right? Then the whole denominator becomes a really big positive number. And 1/that really big positive number would approach 0. So that's a pretty nice property that we can utilize here. Okay. All right. So the outputs from this new type of prediction function, h theta of x, it has clear meanings that we can interpret. Okay. Taking the predicted value y hat, it actually means the probability of that input data points being the class 1. Okay, we have two classes, class 1 or class 0. It's a binary classification, right? And the output function from this h theta of x, it actually can be interpreted as the probability that data points belongs to certain class. Okay, so that will make our interpretation of the results really convenient, right? Given this y hat, we say that, okay, it's y hat percentage belongs to class 1. And if we use 1 minus y hat, it is obviously the probability being to the other class. Okay, so if we have observed a more than 50% prediction, then we are more confident to say that the input should be classified as 1, right? If it's below 0.5%, like a 50%, then we are more comfortable to claim the opposite, right? That is a very straightforward strategy while making predictions. Yeah, so that's really a nice thing about using these sigmoid functions in a prediction, in a binary prediction test, because everything about the output can be explained with probabilities. Okay. All right, so that's a very nice picture we want to have and want to implement. And when it comes to the actual implementation, we need to deal with these practical problems. Like, how do we design a cost function so that we can train the model correctly and properly? Okay, so a cost function, it is a measurement of the distance between the predicted values and the actual labels, right? In linear regression, we use the mean square error, right? We use y minus y hats and square of it and the summation all those squares, right? So what if we have a cost function? Oops, sorry about that. See some overlap. Say if we have a cost function that looks like this, right? Which is exactly the form that we use for linear regression. And then let's substitute this h with the the sigmoid function, right? Which is in this 1/1 plus e to the power of something, right? If we substitute in this function, we actually find that it's actually a really hard problem because this function becomes non-convex and it's hard to take the derivatives of it. There won't be any easy solutions to this problem if we use the mean square error cost function. So we have to define a new cost function that is easy to compute, that is easy to take the derivatives of, and also most importantly, this new cost function should measure the distance between the predicted value y hats and the actual y. Okay, it should serve the function of estimating the costs of certain of the models. Okay, so that is how our final choice for the new cost function looks like. Okay, it's a summation of a long equation in this parenthesis, and there's a negative symbol outside the parenthesis, and within the parenthesis it's actually two terms. The left term here is y hat times the logarithm of the h theta of xi. Okay, so the h theta of xi can also be written as y hat as a short form. Okay, and on the right term, it is y minus y hat times the logarithm of 1 minus h theta of x, which we can rewrite as 1 minus y hats. Okay, so it's actually a pretty semantic equation that we can memorize. Okay, so of course it's a different function from the mean square error, right? So now let's explore several properties of this new cost function, and let's see why it works. Okay. So let's just first look at it intuitively. Okay, I see a question.
Hey, yeah, I had a question.
Yes.
Yes, in the equation, you said it is y minus y hat for the second term.
Yeah, it should be 1. It should be 1.
Okay.
It
I was
should be
just
1.
confused.
Yeah.
Thank you.
Yeah, it's not y. Yeah. So let's see. First, intuitively, how this cost function works. Okay, so let's look at the outputs case by case. And if the ground truth y hat, if the ground truth is 1, okay, so we substitute this y right into this equation, and this one becomes 0. Okay, so we don't need to consider this anymore. So the cost would become the summation of a negative of log y hats, right? It'll be summation of this I omitted this summation symbols here. So it's basically a negative of a logarithm of y hats. Okay, so cost function is something we want to minimize. We want to as small small cost as possible, right? So if we want a small cost and it's a negative logarithm of y hat, which means we want the y hat to be big. Is that right? The cost is a negative of logarithm function, and logarithm is a monotonically increasing function. So if we want the cost to be small, then we want the y hat to be big, which will push the y hat close to 1. Right? We know the y hat is bounded because y hat is the output of a sigmoid function. It's always bounded between 0 and 1. And if we want it big, then we will push it towards 1, which is wanted because we know the ground truth is 1. So it's good if the prediction is close to 1, right? So that's cost function makes sense in the case for y equals 1. And that's another same story. If we have observed a y equals 0, the ground truth is 0, and the cost function will only have one positive term left because this one is 0, and we only have this term left. And if we substitute 0 into here, then it becomes 1, only 1 left. So the cost will be a negative logarithm of 1 minus y hat. Again, we want the cost function to be small, right? Which means we will drives the 1 minus y hat terms big, which in turn drives y hat small, right? So the y hat will be pushed towards 0, right? Which is wanted because it is consistent with the ground truth label. All right, so this is a very reasonable cost function and works on either case of the ground truth label. Okay, so let's further look at the reasons behind the cost function, right? So when we design a cost function, we wanted to give larger penalties to examples or to predictions that are more wrong. Okay, so when the ground truth is 1, right, the cost function looks like a negative of log of y hats, right? Because we have already have the equations as shown in the previous slide. Okay, so if we plot the cost function over here, it is the negative of log y hats, right? It'll be a curve like this. Okay, so let's see. Because the ground truth is 1, and if the y hat is 1, which means it's a correct prediction, it should be no cost, right? Which is indicated by this lower end, the lower right point here. And if the y hat is 0.75, it means, okay, we are 75% confidence that the point should be 1, right? Which is a fairly good prediction, right? But there will be some cost, right? We want the model to be more correct, right? So we will give it some small cost. But what if the prediction is 25% being class 1? Then it's actually a mistake, right? Which means we need to make some relatively big cost to as the feedback to the model, right? And in the most extreme example, if we make the totally opposite prediction, right, then the cost will be super big, will be infinite cost, okay. Right? So that is another visualized reason for using this logarithm-based cost function. Okay, and for the other case, when we have 0 as the outputs, then we'll have the same story, right? When y hat equals 0, the outputs of the cost will be 0 because there should be no cost. And if it's fairly good, then the cost is small. If it's a mistake, then the cost will be big. If it's extremely mistake, then the cost will be infinitely big. Okay, so that's the interesting properties enabled by this logarithm-based cost functions. Okay. So on these slides, we can actually work further on this cost function to see some of the probability meanings. We actually already know that in how to interpret the results. The outputs from the prediction function h theta of x is actually the probability that data point belong to class 1, right? So if we write these two probabilities into a compact format, it actually be the product between this one, h theta of x to the power of y times 1 minus h theta of x power to 1 minus y. Yeah, so because if you let y be 1, then this whole right thing will be something to the power of 0, which is 1, right? So there will be only this part left. And if you let this y be 0, then the left part will be 1, and only the right part will be left. Okay, so this way, the conditional probability is just a compact way of writing these two equations above in parallel. So that's a way to represent the probabilities, right? So given a data set, assume we have m data points, right? Which is m pairs of feature to label pairs or maps, right? So our goal of learning a supervised learning model is that we want to learn a set of parameters, thetas, so that they can maximize the likelihood of the data, okay? And the likelihood of the data is actually a product of all the probabilities, all the output probabilities. So we know that the probability of this likelihood of one data point looks like this form, right? And we just multiply these probabilities with all the data points, right? So this it means that we times up all the probabilities in our data points. So all the x and y's here comes with the superscript I here, right? So it's a very long production, very long product terms, okay? So it's likelihood, and what we can do to likelihood is to take the logarithm of it, right? That's a very common mathematical operation. After we take the logarithm of it, the product becomes the summation. And the logarithm, nice thing with logarithm is that it can eliminate those exponential terms and turns the product into a summation. Okay, when we take the logarithm of this term, the yi would be moved outside, right? Moved off the exponential position, and we have yi times the logarithm of this, and this 1 minus y times the logarithm of this 1 minus. So this is exactly how we define the cost function for the logistic regression at the first place, right? The cost function of logistic regression actually means the negative log likelihood, right? The only difference here is that we don't have a negative symbol here, right? The logarithm of the likelihood is a summation without a negative. So because we want to maximize the likelihood or the log likelihood of the data, which means we need to minimize the negative log likelihood, right? When we add a negative term here, the whole log likelihood term becomes a cost function, okay? Which is basically the same mathematical form, right? And that actually these mathematical connections applies to most of the supervised learning problems. When we design some cost function and we try to minimize that cost function, which actually enable us to maximizes the likelihood of the data over a set of parameters. Okay, so that's something about the cost function. And what actually remains next is actually very straightforward. We can just apply the gradient descent method for training these logistic regression models. Okay. All right. So a little bit review of gradient descent. We want to minimize the cost function in a stepwise style, right? And we need to compute the gradients of the cost function with respect to the parameters. So this is the technical part. We want to take the derivative of a function that looks like this, which contains summation, products, and a logarithm function, and more importantly, a sigmoid function within, right? So this h theta of something is not a linear form, but it's in a sigmoid form, sigmoid function. All right, so that makes the function, taking the derivatives a little bit more tricky, okay? But as you will follow on this slide, you will find actually it's quite doable, quite clear. We have very clear breakdowns here, right? So if we first ignore the summation term and only focus on one item, right? That's within the parentheses. And we want to take the derivatives of everything here with respect to theta. That's what we want to do. Okay, so that is a straightforward step because the h theta of x, exists within the logarithm function. Okay, everything here with respect to h theta of x exists in logarithm function, right? So everything about theta exists in the logarithm function, and logarithm function is a nice function when we take derivatives of it, right? The logarithm term will be gone. There's only it will be moved into the denominator here, right? So it'll be 1 over h theta of x here. And by the chain rules of taking derivatives, we need to further take derivative of the term within the logarithm term, which is h theta of x with respect to theta. And similarly to this one as well, we need to move this 1 minus h theta to the denominator, and there is a negative symbol we need to keep here and take the whole thing, take derivatives with respect to theta again. Okay, so that's a really straightforward step. So all we need to do next, well, here we did another simplification, right? The h theta of x is just the predicted value, right? So we will replace y hat with h theta of x just for simplification. Okay, so it remains to be these two terms that we need to know. It's actually one term, right? They are actually the same term. We just need to know what exactly is the derivative of this h theta of x with respect to the theta, right? So this is the time we need to dive into the sigmoid function. Okay, so it's really at the core of it is the derivative of the sigmoid function. Let's rewrite the sigmoid function again here. It is the g of theta transpose times x. Okay, looks like this. And we again will apply the chain rules, right? We use some intermediate variables, which is z in this case, right? We will denote this whole linear combination term theta transpose x as z, right? So the derivatives of the sigmoid function with respect to theta is actually decomposed into two components, which is first the derivative of g over z and times the derivative of z over theta. Let's solve them respectively, separately. First of all is the derivative of the sigmoid with respect to z, right? And we know the form of the sigmoid is 1 over 1 plus e to the power of negative z. And this one is something we can take the derivatives with principles in calculus, right? So basically, you need to raise the power, the exponential index by 1 into 2, right? if it's in the denominator, right? And also, again, because there's exponential term, it will be remain in the numerator form. Okay, and the second term will be a negative z, the derivative of z with respect to theta, right? And this thing is actually quite straightforward because z is just a linear term. Z is just theta 0, like plus theta 0 times x0 plus theta 1 times x1, blah blah blah. It'll be a like a dot product between two vectors. Okay, so when you want to take the derivatives of these dot products with respect to theta, we actually want to take the derivatives with respect to each component of theta, right? Which means if we take the derivative with theta 0, then only the x0 will be left, right? If we take derivative with theta 1, then only x1 will be left. So anyway, the result will be a vector, right? It will be a vector of x, right? So we can simply write x as the derivative of z against theta, right? So we have now the blue parts and the green parts all solved. Let's put them together, right? The derivative of this sigmoid function against z, against the theta is e to the power of negative z times x over 1 plus the exponential raised to the power of 2, right? So let's do some tricks, which is to decompose the power of 2 here, right? So it becomes 2 fractions, right? And that'll make our next step easier. Okay, and let's further do some decomposition. We just decompose this term into 1 minus 1 over this term. Okay, and we will find that actually we can represent it, right? Because this is our h theta of x, and this again is also h theta of x. These are just the predictions y hats. So we can simply replace these two with the y hats, right? So everything now becomes a very compact form. We can directly use y hats times 1 minus y hats times x as the result of taking derivatives of h theta of x against theta, right? So we are done with the most critical step. And then we just need to substitute this solution back into the previous partial derivative term for the cost function, right? Remember the cost function against the cost function, the derivatives of the cost function with against theta with respect to theta is in this form, right? We just plug in the derivatives into these two dotted boxes, right? That will give us a very nice form, as we will see as we cross out those y hats against y hats, 1 minus y hats against 1 minus y hats, right? And everything left can be like combined into this very compact form, which is the y hats, the prediction, minus the actual label y times x. Okay, I hope this term has reminded you something about linear regression, because it is exactly the same form as the gradients for a linear regression model. Okay, so for the final cost function, the final gradients of the cost function, we just put this summation term back, and it will be 1 over n sum over this difference between y hat and y times x. Okay, so that's pretty much it. And because theta is a vector, so we can put another additional index. as a subscript for indicating which components of theta we are talking about. All right. So it's very similar, right? It's almost the same form as the linear regression. If you looking at the gradients for linear regression parts. Okay, so the only difference is how the y-hat is computed, right? In linear regression, the y-hat is just a linear regression, is just a linear combination. But for logistic regression, we use a sigmoid function to do one more computation, right? We compute the linear component, combination first, and then we put that linear combination results into the sigmoid function. Okay, so that's why the sigmoid function belongs to the type of generalized linear model. Okay, it's just another form of a linear model. Okay, after we have computed the gradients, we just next follow the routines for gradient descent. We initialize the parameters, right? And we will repeat the step, right? Using this formula to compute the gradients and update each parameter using some learning rate alpha, and until we are done. Okay. All right. So that's everything about the gradient descent of logistic regression. And I would recommend you to go through the slides and work on the parts. I would recommend you to work on the papers about the parts where the gradient descent, where the gradients of the sigmoid function are computed. Yeah, it will be really much easier for you to understand the whole mess if you have the derivatives computed manually yourself. Okay, so next we have one last section. We want to go through some notations, vectorized notations. All right. So first of all, there's a slide about the making predictions. Okay. So when we have a model trained, it's very easy to make predictions with a logistic regression because we don't actually need to use the sigmoid function to do the complete prediction, right? We just need to compute this term, which is linear combination, right? Because when this linear combination is greater than 0, right, according to the probability, the property of the sigmoid function, when this exponential term is greater than 0, then this e to the time of something will be smaller than 1, and which means the whole probability will be greater than 0.5. So which means 1 is more likely to be the class. And on the other hand, if we have negative values for this linear term, then the e to the power of some negative to some positive numbers will be greater than 1, right? Which means the probabilities will be less than 50%. So it's more likely to be class 0. Okay, so the process of making predictions is also actually very straightforward. All right. So we had some statistical terms for this linear combination, which is usually called the log odds, okay, or the logits. It measures the ratio of the probability of belongs to 1 against belongs to 0. Okay, sometimes showing the values of a logit will be show better statistical meanings of the model. All right. So lastly, let's look at the notations we use when we deal with large number of data. Okay, so we usually have way more data than the number of features in our data sets. Okay, so the dimensions, for example, in this case, our data points, the features can be n-dimensional, and the y's is actually a binary variable. So when we want to organize everything into computer code, into programming code, then we can use X as a matrix representation. So basically, it can be like n columns, actually n rows by m columns, right? And also for Y, we can also stack all the Y's, all the labels into a 1 by n vector or a one row matrix. So this type of matrix representations will be easier for future neural network models, right? So this will be a convention that we will stick with for the rest of the slides. Okay, so it's a transpose of the previous matrix representation that we used for the linear regression. Okay, but the mathematical nature doesn't change that much. It's just a n by n matrix. You can transpose it whatever you like. Yeah, but here, in order to be convenient, in order to be clear, we will stick with this convention that we put each data examples into columns, into column vectors. All right. And other than that, we also make some new changes to the parameters. We used to use the thetas, right? We used to use the thetas as the parameters, but now we would like to change it to W and B, okay? So the W is short for weight and B is for bias. Weight and bias are the terms that we will use to describe the parameters in the neural network models, okay? But in the case of logistic regression, it's just another way of writing the thetas, okay? So if you use this sigma function to indicate sigmoid function, right? So we used to write down theta transpose times x, but actually now we write it into two parts, which is W transpose times x plus b, okay? So which means we are separating out the bias term or the intercept term, which is theta 0, and the other parameters from theta 1 to theta n. Okay, this makes the meanings of the models clear. In linear model, this theta 0 means the intercept, right? And in generalized linear model, which is here in this case, the logistic regression model, we can apply the same concepts. That theta 0 is kind of the intercept, okay? And this way is easier to for the implementation for future more complex models. All right, and so that means the way we write cost functions also will be different. So the cost function is no longer with respect to theta, but with respect to W and B's. So we can take derivatives of the cost function with respect to W and with respect to B respectively. Okay, so this would also have some advantages to allow us to, we don't need to write a one column in X, right? Remember in the linear regression assignments, we need to create a data set X that are all ones, and then copy the data back from normalized data, right? So this time, if we use W and B as parameters, then we don't need to do that. Okay, and it's also more consistent to a neural network representations in the future. So yeah, that's pretty much everything about logistic regression models. I hope you can work on the derivatives parts for computing the derivatives of this cost function. And also it makes sense if you, it'll help you better understand if you consider two extreme cases where y equals 1 or y equals 0, so that you can find the cost function collapse into very neat, very clear forms that have very clear meanings. Okay. So next, I would like to touch a little bit about the multiple class classification problems, because the real world classification tasks deal with more than two classes. Okay, we want to predict maybe 5 kinds of animals, 3 kinds of weathers, different multiple types of prediction tasks. So these are very practical problems. And the common data sets, like what we had for handwritten image data sets, which is a famous one, it has like 10 output classes, right? To predict customer choices in recommendation systems, we have multiple brands, right? For traffic direction. So in all those prediction tasks, it's actually multiple labels, multiple classes, right? It's way more than 2 classes sometimes. So we need to something more advanced other than logistic regression, because logistic regression only can handle 2 classes prediction. And in this case, we will introduce softmax regression, okay, which is also known as a multinomial logistic regression, okay. And this is the first time that we introduce these concepts, and there will be some math behind, but we will also have a more complete introduction in the future after we have introduced the neural network first. All right, so for softmax, the labels or the classes we need to define is more than 2. So we use 1 to 2 to k, right? It's similar. So it's similar to logistic regression. And the goal is to estimate the probability of a data point belongs to a certain class for each one of those classes. Okay. So if we have such a function that predicts the probabilities written as h of w and b, h of x with respect to w and b. W and b's are the parameters, right? We need to these k outputs as probabilities. And how do we achieve these probabilities is that we will use the exponential function, which is e to the power of this linear combination, right? E to the power of this linear combination. Remember that, so notice that here the w's for each class are different, and the b's for each class are also different. Okay, so these w and b's, they are actually labeled, they are actually matrices. Okay, they are not a very thin vectors. And this vector here is the numerator, while the denominator is for a normalization purpose. It is a summation of all these k exponentials, so that all those values are normalized, right? So that they sum up to 1, which is a valid probability distribution. Okay, so that's how we define the prediction functions. And our w's and b's altogether, they become a matrix. Okay, we will have kw's, k set of w's and b's. All right, so that's a lot of parameters to learn, and we need to define the cost function in a similar way to the logistic regression. Okay, so we will need to use a indicator function, which is either 0 or 1, depending on whether the condition is true or false. Okay, so it is 1 if the statement is true, it is 0 if the statement is false. Okay, so with this helper function, we can define our cost function in a very similar style to logistic regression. Okay, so we put the indicator function here as, and the condition is whether the ground truth label belongs to that class, and also we need to sum over all classes. And this indicator function needs to multiply with the logarithm of the output probability. Okay, so it's very similar to logistic regression. Remember, in logistic regression, we have y times logarithm of y hat plus y minus 1 minus y, right, times the logarithm of 1 minus y hat. So it's actually a very similar form, but we only extend the summation to k classes Okay. And when k equals 2, it will collapse into a logistic regression loss. Okay. Right. And if we look at some special examples, when the ground truth is 1, then there's only one function left, one term left in the summation. In the summation of the indicator functions, right? So it becomes a logarithm of these probabilities of y equals 1, okay? And we will push, by minimizing the cost function, we will push the prediction towards 1, okay? And for the case, if the ground truth is k, then the probability of a k is the only term that we left in the cost function. And by minimizing the cost function here, we will push these predictions towards 1, which is the same logic or the same reason behind the logistic regression, behind the logistic regression loss or cost function. All right. And taking derivatives of this term will be a little more complex, but we can achieve that if we are patient enough on those equations. And it's actually, we will find that the gradients of those multi-class prediction tasks is very similar to the logistic regression. Okay, all we need to do is to handle the dimensions correctly and then substitutes the helper functions, the indicator functions when necessary. Okay. So softmax regression in nature is also a type of generalized linear model. Okay, it's in the same family as linear regression models. Okay, and same thing will applies to the gradient descent for softmax regression as well. All right. So in the future, we will see that softmax regression is so commonly used for multiple deep learning models. Okay, a very typical example is image recognition models or deep neural network models for computer vision tasks. And in those models, we will have multiple layers of parameters that is takes the inputs, the feature as inputs, to combine to compute some intermediate representations, and finally we will need to use the softmax, okay, the softmax to predict the probabilities for each classes. So this softmax is usually applied to at the end of the model, which is a common practice nowadays. So that's my last slide. So I hope this explains the connections between softmax and the logistic regression. And for the assignments that I will release today for logistic regression, softmax regression is not required. You will only need to implement logistic regression. And I would encourage you to work on it. And it'll be in a similar form as the linear regression, but since we have introduced Sigmoid function, the way that you compute the cost will be slightly different. Yeah, and there will be a new data set released as well. The new data set is for predicting rather than predicting the continuous numbers, but it's a discrete binary prediction task. Okay. So any questions? If no questions about the lecture, I will end the class now. And from next week on, we will move back to campus. So, and I will also host a regular office hour on Tuesday morning. So I'm gonna finally see you guys in person, which is nice. And also the future lectures in the classroom will also be recorded. So the YouTube channel will still work and the videos will also be available. Okay. And working towards the end of February, we need to team up with team members to decide the final project topics. Yeah, and I'm working on the final project topics so that you can determine at the earliest points that you are ready.
Hey, Professor, I just had a personal question, nothing regarding the lecture today.
Mhm.
But yeah, I was the one who was emailing you to get into the class. And then I got added on the last day. I noticed like we had a assignment due on February 1st, and I got the class on Canvas on February 2nd. I was
Okay.
wondering if it was okay to turn in the assignment during the weekend. I was
Yes,
just catching up on lectures.
yes, that's fine.
Thank you.
That is okay.
Thank you. Thank you.
Yeah, no problem. All right, thank you, everyone. I'm gonna stop the recording.